Welcome back to my channel, guys. I'm David Mazzei with Mazzei Formula, and this is the MF5 Superlite project. So today's video, we're going to talk about the fantastic drive system that we just finished. This thing took so much work. I'm very excited that it finally fits in the car and everything is working correctly. I want to thank Darren from DLH Manufacturing, who is the engineer that designed this thing in the software and created it with his CNC machines. Thank you so much, Darren, for all of your help and your support all the way throughout this project over the past 2.5 years of developing this thing to make sure that everything is correct on this setup, and for your professionalism and your help. And also Todd Buddy for helping make sure this thing fits in the car that did the chassis fabrication. So what is this thing all about? Why is this so important? What is the drive system? So on a traditional car, you'll see that at the crankshaft at the front of the engine, you'll also have other devices like the alternator, the water pump. It could also be the power steering, air conditioning, things like that, right? Well, the pulleys are all in line with each other, and generally you'll use a tension style belt like a V-belt or a ribbed belt, something like that, that uses tension with an idler pulley or such to create the friction necessary to spin the systems. And so sometimes those belts will squeal. You'll hear like fan belts squealing or alternator belts squealing when they wear out, and you have to rely upon tension to make sure that the devices work correctly. So when you have a big heavy duty alternator, like in the situation of this car, we're going to use a 370 amp DC power engineering alternator, which is like an incredible amount of amperage output. It's more than twice as much alternator capacity than we had on the 4-rotor. Something like that is going to use a heavy-duty 5-rib belt traditionally, and it's going to require a lot of tension and load, and that can put load on the crankshaft of the engine, radial load on the bearing. It's the same thing with a water pump or any sort of devices on the front that rely upon tension. Now, when you look at dry sump, external dry sump engines, a dry sump, for those who are not familiar, means that the oil is not stored underneath the engine. The oil is actually stored in a separate container outside the motor that's taller so that it never has starvation from the G-force changes on a racetrack, right? It also gives you more capacity by carrying more volume of oil that helps you with heat soak and aeration. It gives you better quality to the oil pump that then feeds the bearings in the engine. Now, when you look at traditional dry sump systems, they have to be incredibly reliable, right? Because that's the lifeblood of the engine is oil. You cannot have oil starvation. If you were to have a failure of the bearing in the alternator or the crankshaft or a loss of a belt, it would be catastrophic, right? So if you're going to remove the oil pump that's in the engine and run one external on the engine, you have to have a very robust belt system. So what do these guys use for dry sump external pumps? They use what's called an HTD belt. And this belt is the newest of cog designs. The older design is the Gilmer, which is a square tooth. The HTD is a 8mm profile rounded tooth belt, which this means that every 8 millimeters is a tooth on the belt, And the belt pitch itself, the tooth pitch, is 8 millimeters. It's very quiet. It's very robust. These are also used inside the engines for timing belt systems on traditional engines with camshafts and things like that. And it doesn't need much tension at all whatsoever. You only need just enough tension to keep the belt on the pulley system. So it actually looks like there's something wrong because the belt like slaps around on the slack side, and you can twist the belt so much that it almost looks like it's going to fall off. In fact, on a modern dry sump external driven system like a Peterson or a Daly or any of these popular pumps, you should be able to go up to the motor cold and just pull the belt right off the oil pump pulley without any effort whatsoever. So what we wanted to be able to do is integrate that design for not only the dry sump, but also the alternator and the water pump, because we have a 5-rotor crankshaft, which is custom one-off piece that costs lots of money and takes lots of time to make. And it also has heavy counterweighting to balance out the odd number of rotors. We want to keep the load on the nose of the crankshaft as little as possible, the radial bearing load. So absolutely no tension whatsoever. Now, why is this so important that we get this right the first time? Well, one is because we don't want to hurt the engine or any of the devices, but we don't get a second chance if we break a belt, because accessing this stuff is really difficult. The length of the 5-rotor dictates that we put the front drive cover of the engine basically between the 2 fuel tanks. And in doing so, you can't put the alternator and the pulleys and all the stuff up there. And even if you could, it's hard to access that. You'd have to take the roll cage out and you'd have to take the body off the car in order to fully access all of this equipment. So it's something you want to get right the first time. It's something that maybe you change the belts after 50, 60,000 miles. It's not something that you want to be messing with, trying to set your tension on the alternator, burning up a belt, replacing an alternator bearing or a pulley. These kind of things need to be robust, just like the oil pump. And because it's having to be fit between these 2 large pieces of the fuel tank, like it's essentially 2 fuel tanks that are connected with transfer tubes, we need to be able to mount these pumps and these devices in remote locations on the engine. So the dry sump pump is actually mounted midway back on the motor itself, and then the alternator is actually mounted about 1/4 of the way back on the engine, because you can't fit them inside the bulkhead and between the fuel tanks. And then we have these custom-made drive shafts. One that's an extension shaft for the oil pump, which uses a drive coupling that is spec'd out to the specifications of the torque load of the dry sump pump itself. And then we also have one that's specially designed for the alternator as well. And then these have captured bearing plates that offer additional bearing support for the elongated shafts that then spin the respective devices. So look, it sounds super complicated. It's best for me to just show you what's going on here. And so let's get into the video. So the first thing is we got the 5-rotor block installed in the car. My buddy Tim Nevins helped me install it. There's nobody I trust more than him. He's one of my best friends. He crosses all of his T's and dots all of his I's. He's actually an Air Force mechanic. And so I'm really thankful for his help and his expertise of how deep he goes with the tools and everything that he does. So we got the engine installed in the car. You can see that in the last video. And the next thing was I needed to take this alternator and get it converted to external regulation. One of the things that likes to go out in an alternator first is the regulator, and then the rectifier and the stator. So I wanted to go ahead and get the regulator deleted to where it could be externally regulated from an external box, because that could handle the heat better, because it's not trapped inside the alternator. Plus, it gives us a multitude of options when it comes to battery voltages. We can run a 12-volt battery, a 14-volt battery, or a 16-volt battery, and we can adjust the charging voltage to whatever we want it to be. In this case, we're going to try using a 14-volt static battery that charges at 17 volts. That's going to give us less voltage drop across the chassis. Well, by the time the voltage does drop in the DC system, we still have a high voltage when it gets to the devices that we're trying to power. So I took the alternator to this shop called Southern Armature, which is in Birmingham, Alabama. They've been around since the 1920s. They do a phenomenal job. They did this for me on the last alternator. And this alternator was a little tricky because it has a hairpin style stator. It's 370 amp. It's kind of sophisticated inside, and you can't just wire the field wire directly to the stator. So he had to go through some things, but a gentleman over there figured it out, and he gave me an external wire that I can run to power the field current off an external regulator. So I'm really thankful that they were able to do that. Then the next thing was I wanted to make sure that the transmission was going to match the paint on the engine. I had already painted the transmission, and I used like a high temperature aluminum color paint, but I just don't think it matches very well. It's not very artistic when you plug it into the back of the engine, because the engine is billet plates with powder coated silver housings. So instead of just using the paint that I had already painted the transmission with, I decided to take it back outside, tape it off. I spent a few hours going over it again, and I painted it silver and then clear coated it. Now you can see it looks super nice, and it's going to match with the contrasts of the engine. Now I'm waiting on a part from Hollinger that's going to change the air gap. I wanted a little more air gap between the hydraulic throwout bearing and the clutch pack assembly to make room for the fingers to move back during the wear of the clutch. And so I'm waiting on that fulcrum point to then press back into the throwout bearing so we can increase our air gap. So that's why the transmission is off the car right now. But super excited about that, and we're going to go over the Hollinger transmission in future video. So then the next thing was, we have this custom drive hub and crank mandrel that Darren has also made for this engine. What this allows us to do is basically have the HTD profile to drive the alternator, the water pump on the front section, and then on the outward section we can put whatever size pulleys that we want on there to mess with the ratios that we're trying to get the best belt and drive ratio between the oil pump and the engine. And in this case, we try to target somewhere around 50%, meaning the oil pump runs at half the speed of the engine. So go ahead and mock that up. I use mock-up hardware, and then I'm going to come back and use titanium and stuff that's super lightweight, like the bolt on the end. I want to use titanium because it's an M12. It's like 40 millimeters long, and it carries a good bit of weight. I want to reduce the amount of weight that's on the very end of the crankshaft. So we're going to put a titanium bolt in there, and then also the screws that hold these hubs together. I also want to use a 12.9 steel Allen head. But just for mock-up, this is what we put on right now. So then the next thing was to test fit the fuel tank in the car. And you can see that the fuel tank lays right over top of all this stuff, and it is a bit tight, but there's just enough room for everything to function happily. You just have to make sure you get everything correct. Now I'm probably going to take this tank out and reinforce this opening area with either carbon fiber or more aluminum, some sort of structure to where if we were to lose a belt, it wouldn't slap against the aluminum directly. It has some sort of cushioning, kind of more like a firewall nonetheless. So we're going to get into that later, but you can see it all kind of fits. Then the next thing was I wanted to paint the cooling lines that are on the motor. Now these cooling hard lines were done by Todd, and you can see this is the line that comes out of the water pump and feeds the inlet of the motor. I put the water pump right here and have a direct pumping straight from the pump directly into the engine, because this is where we want the highest amount of volume and flow, because we're going to increase the block pressure as much as possible to decrease the nucleic boiling that's inside the engine, also known as like hot spots. So you want to have the highest amount of block pressure in the engine, because the more pressure you have in the engine, now I'm not talking about the cooling system pressure that you would see from thermal expansion and your pressure cap. I'm talking about actual like pressure that's generated by forcing water through the engine versus it coming out of the outlet. We want to keep that as high as possible, because that's going to help minimize hot spots around the spark plugs and things like that. So this is the return line. I painted this. I did a 2K gloss black outside. Looks pretty nice. We're shooting it outside just like the transmission. Then the next thing was to test fit the side bracket for the water pump and all the accessories. This side bracket is very integral to everything. It's pretty thick aluminum. It's billet machine 7075. This is going to use all of the factory mounting bolts, which is M10s and also like an M12. So it's very, very strong, and the drive plates bolt to this side bracket. So then after we make sure that all that fits, then we're going to mock up the hoses or the lines and all the stuff that feeds the rotors themselves. So I've got another cooling line that's not just the return line out of the engine. It actually is a second branch off the outlet of the water pump that's going to individually feed each rotor housing. I'm not going to use the front one because it's not really necessary. It's already getting so much water pressure from being at the very front of the engine, but this is going to radially feed the rotors next to the spark plugs, again, to try to reduce those hot spots. Okay, so go ahead and mock that up, and I'm playing with different hose designs here. This is something that is just trial and error. Basically, the alternator drive shaft comes through here, and you have to make sure that this hose design can clear that alternator drive shaft. So I went through a few different designs. You'll see me try it throughout the video different ways, but I wanted to be able to pull the alternator with the drive shaft attached, so I don't have to sit underneath the car and hold, you know, a screwdriver in the fan of the alternator and try to spin the flat of the drive shaft and pry this thing apart. If I could just unbolt it from the front where the pulley bearing assembly is and pull the whole thing out, that would be great. So that's the reason why I've kind of deleted this hard line and put the soft line in here. Plus, it gives us a little more flexibility around the fuel tanks. So we don't have to worry about things touching if we have soft lines. The next thing is on the outlet of the engine is where I want to measure the water temperature. Now, I guess you could measure the water temperature when it comes into the radiator off the return line, but I want to measure it directly exiting the engine because this is going to give me like the best data for what the actual temperature is inside the block, right? Because it hasn't had a chance to cool off as it's heading towards the radiator. So I tapped the 16AN fitting on the edge here that seems like there's enough meat and it should work great for an 1/8 inch MPT fitting, which I'll put the Haltech sensor in a little bit later. So then we've got the return line installed, the one that was painted earlier. And then I realized that, you know, I needed to weld a fitting on for the rotor feed line that I was talking about a minute ago. So I took this rotor feed line over to my buddy Tim, who I talked about earlier, that helped install the engine. And he is a JDM collector. He also builds motorcycles. He does all kinds of things mechanically, and he's a great TIG welder. So Tim helped me weld 10AN fitting to the end of this so that I can come off of the water pump and feed that rotor cooling line and have flexibility to try these different designs. Okay, so after we went ahead and did that, I also painted the crank angle sensor cover and installed the temperature sensor, which you can see here. Just a nice little extra touch. Obviously, you're not going to see all this when the fuel tank is in, but it's an art project and everything needs to look great and everything needs absolute attention to detail. So, of course, we have to paint the crank angle sensor cover. Okay, so then the next thing you see here is I'm mocking up the brackets that we made. Stan Levine and Walker Morgan, we came together and designed these brackets for the ignition system. This allows you to hold 2 IGN-1A coils, a trailing and a leading, or a CDI coil as well, or both CDI. They're interchangeable, and allows you to mount them on top of the rotor housings themselves. And you can see here the little ceramic spacers that we use to help reduce heat soak into the coil. Now look, it's not the most ideal location for heat, but it is great because it allows you to fit everything that you want on the engine and in the engine bay. If we had to mount all these coils elsewhere, we wouldn't have room. So it keeps everything nice and compact. I don't think it's going to be an issue for heat. I've had people bring that up in discussion, but this is where I ran the coils on my 3-rotor engine. And this is also where the Mazda factory puts the coils on their race cars, including the 787B. Okay, so I don't think it's going to be much of an issue, guys. And if you're interested in these brackets, you can head on over to www.mpfab.com, Walker Morgan's website, and you can order these brackets. They will go on your rotary engine, and I believe they will clear most of the oil filler necks that are aftermarket. If not, it may just require a little bit of modification to your oil filler neck. But for the most part, people have not been having problems with these, and they're also now slotted, so you can kind of move them around respective on each rotor housing. So the reason why we have CDI ignition and IGN-1A ignition is because the CDI is going to offer a heck of a lot more spark energy to help us ignite the fuel mixture, being that it's a peripheral port and we're going to run E85, and we may want to run it richer than what most people do. And then it'll also allow us to fire through the great amount of water injection that I'm going to put in the engine. Why am I not using methanol? Because you only really need to use methanol if you don't have enough spark and you're trying to substitute water for a more flammable liquid. So if you have enough spark, then it's always best to just use water. You're not really going to lose power if you have enough spark, because then you can advance your ignition timing and you can increase your boost to offset whatever power loss you incurred from the degree of water that you're adding. But in the end, it still benefits you because your knock suppression is much greater by using straight water. Now, the next thing I'm doing here is I'm test fitting the alternator drive again with a new setup here. You can kind of see how this works. Then I'm painting the rear drive plate. And then I'm going to install the cooling feeds on the car and the rear drive plate. So you can kind of see it all going on here. This is where it's all kind of coming together. And like I said, a lot of this stuff is like trial and error. You fit things on, you measure things, you order fittings, you send them back, you cut hoses. I get mock-up cheap hose on Amazon. I test it out, make sure it works. Then I take it back off, order the expensive hose. There's a whole lot of trial and error that goes through. It's kind of like Russian roulette. Like, I'm going to order 15 of these and maybe 5 of them will fit. you know, maybe I'll get lucky. So that's just how this goes, man. You can try to model all this, but you'll be there all day trying to draw these things. So it's best to just actually try as you go and see how things come out. Now, this is something that I ran into as an issue that we didn't catch earlier. The water pump has a guide on it, which was going to help protect the belt from coming off because we're going to run so little tension. But running this guide on the alternator or on the water pump doesn't work too well because when you put the guide on there, it actually spaces the pulley back a little bit from center line with the crankshaft. So because we already have a guide on the alternator and we have a guide on the crankshaft, I looked up the papers on how HTDs are supposed to work when you're driving more than just one accessory. And what you're supposed to do is have a guide for every other device. So as you can see, we can remove the water pump guide and we're still fine because we're guided by the alternator and we're guided by the crankshaft. So I took the water pump over to my buddy John, who pressed the pulley off. The reason why it is press fit is because it's not specifically designed for the water pump. Usually the water pump uses a tension design, and getting it to fit, it was a little bit of a tight clearance. It just doesn't want to go on and off easily, but it's okay. We pressed it on, got the guide off, and put the new pulley back on. So now we've got this water pump back on the system. Now, what is the significance of this water pump? Why this water pump? Well, the rotary engine doesn't really have a lot of water pump options. When most people run out of the flow capacity of the factory water pump, they end up going to an electric water pump. Now, electric water pump's really cool because it provides a consistent flow rate all of the time. Okay, so when the car is at idle, you're probably getting a lot more flow than you would from a traditional pump when it's, you know, idling because it's belt driven, right? So you can get a lot of flow all the time out of the electric water pump. However, the problem is the electric water pump has to deal with the back pressure of the engine block and all of your lines. So when you run an electric water pump through your radiator, even though they're rated at like 55 gallons a minute, right, which is almost a gallon a second, you're not going to get anywhere near a gallon a second. You might be lucky to get a quarter of a gallon a second. And that's because electric motors, they just lose capacity in flow and volume and pressure as soon as they get head pressure against the nose of them. So if you wanted to get 55 gallons a minute out of an electric pump, you'd have to use like 24 AN lines, and there'd have to be like no bends, and it would have to just be crazy massive lines. So we want to get lots of flow. So the only way to get lots of flow, the only option is to get a robust, crazy water pump. So this water pump is from Mazzei, and this thing is a bad MF for the MF5, okay? And so we had to fit this thing in here. It barely fits, barely clears the bulkhead for the car. It's got a 20 AN that comes into the bottom of it, 24 AN lines that go down the car, comprised of hard lines and soft lines, and we've got 2 radiators in a series. But this thing is going to move some serious water. And then not only do we have this, but we also have the most powerful electric water pump that you can feasibly buy, the CWA 400, which is a 40 amp unit. And this thing is actually going to feed the inlet of the mechanical pump to make sure it doesn't cavitate, since it's having to pull uphill and it's having to be necked down to a 20 AN from a 24 AN. So we should be able to move some serious water in the car. Now, the only thing about installing this water pump is that this line just doesn't quite want to move around this chassis support bar here. It is getting pressed on just a little bit. Now, it's not really concerning. However, because this stuff is not very accessible, I don't want to run the risk of this line collapsing. Now, this is braided AN line, and I'm using a very strong brand. This isn't your typical nylon braid. This is the Frigola 20 AN line, which is rated for 28 inches of vacuum, okay? But I still chose to install vibrant springs inside the line. This is an anti-collapse spring, which means that under vacuum pressure, if the pump draws 28 inches, which is almost a perfect vacuum, it won't try to crush on me. And then also because it's making this kind of weird radius around this edge here, it won't kind of push in on the hose and cause any sort of turbulence or issues. Now, the spring does reduce the volume that the line can support. It's going to cause some turbulence, but the pros outweigh the cons. I think we have enough water pump between the electric and the mechanical to override any sort of drop that we may incur from this short bit of coil that's been put in the hose itself. And I also want to thank my friend Brett in Australia for kind of running these ideas back and forth with me and make sure this was the right way to go. So then I'm going to test fit the alternator again. And I've also got this shim that I had to make with these washers. I kind of grinded them down on the vise. Not really the most professional way to do things, but sometimes you just got to get things done. As long as things measure up correctly, you're going to be good to go. The real engine is a little bit wider than the dummy block because the front iron of the Billet Pro plate is slightly thicker than the iron that we had on the last engine. That doesn't mean there's anything wrong with either one. There's just a slight discrepancy. And so because of that, I had to make a shim that's exactly 1.7 millimeters so that the bottom support plate and the top support plate are perfectly in line, and that when you bolt all of this stuff on, it's all lined up correctly. Now, this isn't going to affect the alignment of the water pumps and the alternators and stuff like that. It's just the relative alignment of that whole system to the block. I just want it to be perfect if possible. And so then I had to do the same thing with the oil pump. Whatever shim I applied to the front system needs to be applied to the oil pump, which is on its own separate bracket, so that we don't have parallel misalignment. Now, there wouldn't be any axial misalignment and there wouldn't be any angular misalignment, but there would be a little bit of parallel misalignment of almost 1.7 millimeters. So now that we have that shimmed out as well, you can see that the drive shaft for the oil pump and the extension shaft that's coming from the oil pump pulley at the nose line up nearly perfectly. It's so small of a misalignment that I can't even really get a feeler gauge on it. So we're within the tolerance margin for the coupler that we're going to use. Now, the coupler that you see that's on here is a Lovejoy coupler. This is pretty common coupler that's used. There's many different versions of these in different sizes, and it allows for a slight degree of axial, angular, and parallel misalignment, and it has what's called a spider in it, which is a rubber cushion, and these teeth lock together. It's sort of like a fail-safe design, so if the spider wears out, the teeth will still grab each other, and this is how you transmit power between two shafts, traditionally speaking. But because of the fact that this oil pump, being that it is a massive 6-stage with 2 pressure sections, it has me a little bit concerned because it could draw more horsepower and incur more load because of all the volume of oil that it's trying to pump, since it is like double the size of a pump than a traditional dry sump, that maybe we need to have a stronger coupler. So I talked to Darren about it, and he's like, look, if you can fit it, then it's no harm in trying. So I got this coupler, which is made by, I believe it's made by Temkin, and you can see that here in the video. This is a really bad boy coupler here. It has a white urethane spider inside, and it also has a retaining collar that goes over it with a snap ring. Now, that was kind of fun trying to get that snap ring on. It's a really big one, about 2 inches, but this thing can handle almost 50 horsepower of load. So not really worried about this becoming the weak link. If anything is going to break, it's going to be either the oil pump shaft or the extension shaft, which is highly unlikely if we set everything up correctly, especially considering we're using a really large bypass thermostat so that we're not having to deal with all that pressure on cold start. And then also we have 2 independent regulators on the back of the oil pump, which I'm going to maybe experiment, if necessary, with using a check valve on one of the pumps so that I can create my own curve between both pumps. That way we don't have too little pump, and that way we don't have too much pump. It's really hard to adjust the flow rate of an oil pump. And you know, if you adjust the pressure from the regulator, okay, well, that sets your bypass limit, but you could still have that same pressure at idle. Like, so if you're targeting 130 PSI, you don't want 130 PSI at idle also. And if you're getting that all the time, then it means you have too much pump. But in this situation, since we have 2 pumps and we know one is probably on the edge of being enough and 2 might be too much, we can be somewhere between that by adjusting one of the bypasses on one of the pumps and utilizing a check valve. We're going to experiment with that later, but first we're going to fire the car up just as it is, with the settings being similar on a lower PSI spring, somewhere around 60, 80 PSI, just to see how things work, and then we can go from there. So then you can see everything is put together now with the belt system and the tensioners, and you can see here that we have a tensioner. I'm sorry, I keep referring to these as tensioners. They're actually idler pulleys. And what these idler pulleys do is they help to increase the contact of the teeth on the pulleys themselves. They're not actually there to apply tension. You could apply tension with an idler pulley, but we're not doing that. So essentially, the idler pulley, like you see on the alternator, is just giving you more wrap and more mesh with the teeth on the water pump so that you don't put so much load on the very few teeth that you do have. And so there's really hardly any tension. You can see that there's about 110 degrees deflection on both of these belts, then because we had so many different combinations that I ordered in belts and pulleys and did a bunch of math calculating different ratios, I was able to find the perfect ratio to where I didn't even need to use the idler. I didn't even have to worry about it. It had just enough tension where it slides onto the belt and it can be turned 110 degrees. It's sloppy just enough to where it's not going to load the crankshaft, and it's also not going to fall off of the pulley system, that I don't believe we need to use a tensioner. And so I prefer to try that rather than use a tensioner, because this is how you traditionally set up a dry sump. Not to say that the tensioner or the idler pulley, whatever you want to call it, won't work. It's just that it's another thing that could fail, another bearing that you don't want to have to worry about screaming at 20,000 RPMs between your two fuel tanks. So you can see that all this has come together. Now I'm doing the final assembly of all the lines. Dry sump lines look absolutely crazy. They're coming out 150 degrees under the pump, running over top of the pump back into custom banjo bolts that I had machined in Australia for me. So these banjo bolts have a really short nose on them so that the hose end isn't super long, and that allows you to run the line in close proximity to the pump and make it all around the top without getting in the area of the spark plugs. You can't run the lines under the pump because the pump is already so low that your lines would have to loop down under the chassis, and they'd be like, you know, a risk for like hitting the road or something like that. So we run them over the pump, which is pretty crazy looking. Now, this was something that I was slightly concerned about causing a potential airlock situation, but after talking to multiple dry sump manufacturers, we believe that this is going to work fine, because these are only for the scavenge stages of the pumps. So the pressure sections of the pumps are going to be pulling oil from the tank, which is uphill from the pump. The scavenge stages are designed to pull oil and air, and they're all connected together and manifolded to a single outlet. So as long as one gets a little bit of oil, it'll seal all the others. So we're not really worried about that. And you can see it all just beautifully fits in here. Now, again, this is like so many hours. This has been the past 6 to 8 weeks of trying to figure all this out. And I also want to thank Walker Morgan, because we were looking at this on his lift and just scratching our heads trying a bunch of different designs about a year ago to kind of game plan for this situation right here. And it all worked out just great. Again, I'm using the Fergola nylon race hose, which is 28 inches of vacuum rated, does not require a spring, and it's one of the only premium nylon hoses out there that you don't have to worry about collapsing. Generally speaking, you would see someone use a stainless steel braid, or they use a PTFE line or a crimped hose or something like that. I like the ability to use these nylon braided hoses because I can assemble them myself here. It's not extremely expensive, and I have so much trial and error that I have to go through that there's no way that I can go and get like a NASCAR Formula One level hose just like made for me. I have to test fit all of this stuff first. So this is something we can get running on, and then we can move to higher quality equipment later. But this allows me to try multiple different angles and cut different sizes and all sorts of things so we can keep the project going. So then you can also see the jam nut that I installed on the back of the alternator here. I cut the bolt down a little bit and put a jam nut that's a special locking jam nut on here that I got from Bell Metric. Doesn't seem like a big deal, but it is, because the last nut was a little too tall and is pressing on the hose too much, and that concerns me. Again, I can't take any chances on these systems. So everything has been like Loctited using green and blue Loctite, torque specified with inch pounds. Everything has been gone over perfectly to make sure that we minimize any chances of failures on this belt system. All the alignment, all the design work, all the drawings, the bearings, the assemblies, all of this stuff, the thermal expansion, the torsional load on the shafts, all of this has been taken into consideration over and over and over for the past 2 years. So I'm very excited to be able to put this in the car. And then the last thing you can see I'm doing here is making the ignition wire leads for the IGN-1 and the CDI system. Now, again, this is something I may upgrade to higher quality 10.5 millimeter suppression wires later, but it may not even be an issue with 8 millimeters that we have on here right now. But I just wanted to get the layout as effective as possible. There's a whole lot going on under here. You can see all the oil feed lines that feed all of the bearings for the engine. Now, it looks like these might be a little bit small to be feeding all of these bearings off of a Dash 10. However, you have to also remember that the oil runs through the engine and out the front cover as well, the front plate. So we're actually like, this oil chain is being fed from both the front and the rear from the Dash 10 that fills it. So we kind of eliminate a pressure drop across the engine, and it kind of equalizes the pressure through that line. So There's a whole lot going on, my friends. I'm super excited. We're going to keep moving forward on this. The next thing up is to finish up these scavenge lines on the oil pump and then start moving on to the pressure lines. And then I'm also going to be pressure testing all of those lines, pressure testing the cooling system, pulling off a few of the hard lines that need to have some fittings welded up on, then painting all of that stuff, painting the radiators, putting the fans in the back, buttoning all this stuff up. And then we're going to be ready to start putting on the intake and the exhaust manifold and the turbocharger and all the fun stuff, the transmission, all that. But first we want to make sure we get all these integral components finished up and finalized so we don't have to worry about these, and it'll make for a reliable platform. That's what this is all about, is enjoyment, reliability, and artwork. Mazzei Formula 5. And if you're interested in a drive system like this for your rotary, whether you have a 13B, a 3-rotor, or a 6-rotor, this should bolt on any engine that uses FD style front plates. And you could use any timing cover that you want, really. And we also have a design that we use magnetic crank pickups. I'm using the mechanical crank sensor just because it's simple and easy. I'm used to it. So just contact me on Instagram and I can set you up with our design if you're interested in this. And again, if you're interested in the coil brackets, you can get them from Walker Morgan's website, mpfab.com. So thanks a lot. I'm looking forward to finishing up this project. I'm hoping to get this thing running by the end of this year. It's been so much work, but I'm very thankful for all of your support, all of my sponsors, everyone that's helped in this process. This is an incredible journey, and I'm so excited to keep plugging ahead. I'm David Mazzei with Mazzei Formula. Y'all have a great one.